Okay, students, I've been looking at your practice B for some of the first few people who have submitted it, and I've decided there's a couple of these I probably need to work through like I would have in class to help you out a little bit. So we are going to start with a few. This is page 313, practice B. We're going to start with problem number 2. I did not try to draw a 3D diagram here, but what I do have is a diagram of the base of this figure. The base is what would be parallel here. So let's see if we can't write on this. This side, according to your book, is 2.4. This side on the bottom is 3.2. It does not give you this diagonal, but it tells you this is 1.6. And some of you might have recognized this as a trapezoid. If you did and pulled out area of a trapezoid, I'm proud of you, but I usually don't even use area of a trapezoid for this. What I'll do is I'll just draw a line and split that into a rectangle and a triangle. I apologize, my line's not straighter, but I have a rectangle and a triangle, and I can separate them up. And if I do this, I can see that this part here is 1.6 because the top up here is 1.6. And if the whole thing was 3.2 and that's 1.6, this side on the right is also 1.6 because these two 1.6s would add together to your 3.2. Anyway, but once I subdivided that, I'm ready to find the area of the base. So my area of the base is going to be 1.6 times 2.4. That gives me the rectangle part, and then I'm going to need to add on the triangle part. The triangle part is 1.6 times 2.4, but since it's a triangle, it's also going to need a 1/2. So if you put that in to Desmos or something, you should come up with a value of 5.76. And this would be the area of this entire trapezoidal base here is 5.76. Now, once you know the area of the base, the volume is just going to be your area of the base, 5.76, times your height of 3. And then that should give you your final answer for your volume. Should be pretty easy to get it from there. On this next one, this is number 10. Number 10 was this weird shape here. And once again, I have to find the area of the base and the height. Once again, so this was 5. And let's see what we can get going here. 5 and a 5. And it also turned out, if we had the diagonal drawn, it was 5 deep, but we're just concerned about the area of this base. Now, several of you were able to say that this is 25, but you weren't sure what to do with this thing at the top. Well, notice this thing at the top is a semicircle. So this distance here and this distance here are the same, and so is this distance. So since these two things are equal, I can tell you that both of them are actually going to be 2.5. So this radius of this semicircle is 2.5. So to find the area up here of this semicircle, it's going to be pi r squared would be the whole circle. And since it's a semicircle, I'm going to do 1/2 times this. The reason for this 1/2 is I do not have the whole circle, just have half the circle. So that would give you the area up there. I think when you were to do that, then you could just put this together and do 25 plus in terms of pi, it would be 25 plus 1.25 pi. That's your area of the base. And then you could just multiply that by your height to get your volume for this figure. You could have also done the volume of the cube and then the volume of a half cylinder and added those together. That would have been an acceptable way to try that one as well. One more I wanted to talk about with you was number 11. On number 11, they said they had a fish tank. And once again, I didn't attempt to really draw the entire 3D diagram of this fish tank. Oops, didn't mean for that to happen. But if I were to draw it in, you would basically have the fish tank going diagonal like there. And the depth they told you of this fish tank was 24 by 12. And then the entire height here was 18. Now they told you they started by filling it halfway through with water, so it's got 9 inches of water, and you were probably pretty tempted to go ahead and do 18 times 24 times 9 and get the volume of water in the tank, and there'd be nothing wrong with that. But I've got a little shortcut way to show you. Basically what they have done here is they have just said they've dropped in a rock, and the water area raised just a little bit. Let me see if I can get this to cooperate. So that's basically your new water area. And basically this new water only went up by a small amount, by 0.5. So all you really care about is the height of the water that was increased when the rock was placed in. So basically your volume of this rock is going to be your 24 by 18, which is your area of the base, multiplied by the height. I'm sorry, this was not 18, this was 12. That's going to make a big difference. Let's change that. That should be 24 times 12 there. So 24 times 12, and then multiply it by the height of water caused by adding the rock. You could have found the height of water before the rock and the height of water after the rock and subtracted, but this way would also be acceptable and get you the answer. And the last one I want to look at, if I can maybe just get a little bit of blank space to write on one of these, is number 9. On problem number 9, just going to work it over here. It has basically given us a volume of one shape that was 112 pi, and then it's wanting to know the volume of the other shape, and it did not give us all the dimensions. It just told us the radius of this shape was 4, and the radius of the new shape is 6. This goes back to something we were talking about when we were doing the ACT prep work in class, that if you have this ratio of the figures, you can say that these figures, since they're similar, are in a 6:4 or a 3:2 ratio. Well, if the ratio of the sides is 3:2, the ratio of the areas, I would square that, and the ratio of the volumes, I would cube that. So my volume ratio, I'm just going to call that VR, is going to be equal to 27 to 8. Because if the original sides had a 3:2 ratio, I can cube both of those, since a volume is a side cube, and that would be a 3D unit. So I cube all my units. So I take 3/2, cube it, I get 27 over 8. And then what I can do is just multiply this 27 over 8 by my original volume and get the new volume. And that's why you didn't have to have the height of those cylinders or worry about what that was. You can just use the ratio cubed, since it's volume, and do that. If you were dealing with surface area, instead of using the ratio cubed, you would use ratio squared. And that holds for any kind of 2D or 3D shape. If you can figure out the linear dimension ratio, if they're similar figures, you can square it to get areas or surface areas, or cube it to get volumes, and use that ratio to solve your problems. I hope this helps you on practice B for lesson 8.4, and have a great day. Don't hesitate to let me know if you have any questions.